Hello all, welcome to this lecture series. In this lecture series, I'll talk about very briefly and broadly about a current open problem in data science and in machine learning. First, I'll walk you through the problem, I'll introduce the problem, kind of tell you what it is, and then I'll provide some resources that offer some solution to this problem. But and even though there are some solutions to this problem, it is still an open research question. As you already probably know, artificial intelligence and machine learning form a large chunk of data analysis. Like, it's not the entirety of data science, but they play a very important role in data science. So let's talk about artificial intelligence. As you also probably know, that we humans, we have been we have been working on artificial intelligence for a long time now. And the entire purpose for this field is to create automated programs that can make decisions and reasoning like human beings can. Okay, and it was our pursuit of artificial intelligence that led us to machine learning, and it was machine learning that ultimately led us to deep learning, which is right now leading the frontier of AI. However, one problem we have with deep learning is that, like many other machine learning algorithms, they are what are considered black box models. Okay, so what do we mean by black box model? Okay, in order to understand that, let's just take a step back and see how a human being would make a decision, or how a human being identifies objects. Okay, so suppose a human being was given the images of the peach and the apple on this slide and asked to identify which is which, right? The human beings will probably note that they were both has a round shape, they are reddish brown in color, and they both have a stem sticking out of them. However, the human beings will also realize that one has a duller appearance, is more on the orangish yellowish spectrum of colors, whereas the other is shinier in appearance and is more dark or bright red than a dull color. And also the human being will probably remember or have memories of having a peach and apple, and they will realize that one is softer than the other, but also that one is probably a little bit more sweeter than the other. So the human beings will draw on their experience and use this experience and attributes like color and texture and taste to make the distinction between an apple and a peach. However, when a black box model is making a decision, okay, we don't have any of those information. We don't know what attributes they're looking at. We don't know what features of the object they're looking at, or what they're focusing on in order to make their decisions. We do have a mathematical model that kind of tells us the calculation the model is making to come up with their decisions, but the mathematical model does not tell us or doesn't map back to the reality of the objects that we understand, that we as human beings understand. Okay, and in the best case scenario, what can happen is that the black box model making the decision makes the right decision. It labels the peach as the peach and the apple as the apple. However, once again, even when they're correct, right, when they're making the correct decisions, we do not know what attributes it's looking at. Okay, and in the worst case scenario, where it messes up the label, it makes the wrong decision, it becomes even more problematic because we don't understand why the model is saying the peach is the apple. We don't understand what attributes it's looking at. There is something wrong, definitely, but we don't know how to fix it. And these kind of misattributions can become very costly, especially when the model or the black box model is trying to help a physician decide what kind of treatment a patient should get, or whether a patient has diabetes or not, or even whether a bank should give a person a loan or not. Okay, so these kind of misclassifications or misattributions, or whatever the reason they mess up, can become a big problem when the machine learning models or the black box models are applied in society. Since we don't know why a black box model makes the decision that it ends up making, it is very problematic for us, and this gives rise to this open question that I wanted to talk about, which is about making a machine learning model either interpretable or giving them the ability to explain themselves. Okay, so in this section, let's just briefly go through what are the different kinds of machine learning model and what we know about what is the current state of machine learning models and interpretability. But before we dive into machine learning and interpretability, for those of you who have not had the opportunity to explore machine learning yet, let's just talk briefly about the different kinds of models we can have in machine learning. And the two broad classes are supervised learning, or models that are trained using supervised learning methods, and then there are the unsupervised learning models, or the unsupervised models. So what happens in the supervised learning paradigm is that we give the model data. We give the model data and we tell the model, hey, you are now looking at an apple. The data you just got, this is an apple. The data you just got is a banana. The data you just got is a mango. And then if the model, and then this way we teach the model, and when the model makes a mistake, we penalize the model, and we keep giving them data until the model gets it right, or at least that's the idea. So what happens is that when the models, after the model has been trained and is done with learning, if the model sees a new data point that is similar to the data points it has seen, it can then go ahead and classify it as an apple and say, hey, look, this is a new data point I haven't seen before, and even though it's green, I know it's an apple. Whereas in unsupervised learning, what happens is that we do not tell the model or provide any guidance to the model. Like, we do not tell the model that these two fruits are apples, or these two fruits are a banana, or these two fruits are mango, right? We just give the data to the model, and then the model works its magic, does some computations, and finds that the two apples have attributes that are close or similar to one another, but that are very different from the attributes it obtained from the banana and the mango, right? And the same with the attributes of banana. It is similar among the two banana, but different from the apple and the mango, and so on and so forth. And the output of this model, the model still doesn't know that this fruit is the apple, this fruit is banana, this fruit is a mango. But instead, what it does know is that this group of fruits has attributes that are similar to one another and different from the other two. Okay, and that's called unsupervised learning, and clustering makes up a lot. And usually the other name you'll hear for unsupervised learning is clustering. And there are a bunch of other machine learning model or training paradigm that has come up, like supervised learning, active learning, transfer learning, weak learning, and I encourage you to go ahead and explore each one of this. But supervised learning and unsupervised learning are broadly the two large classes of machine learning models. Okay, and it's enough if you understand this too for this lecture series. Okay, so now that you know what supervised learning and unsupervised learning is, what I have here on this slide is a list of models that are used in supervised learning to make predictions or to classify objects. Okay, and some of these models are the linear models, or you may have heard them as linear regression or logistic regression. Then there are decision trees, random forest, KNN, support vector machines, and so on. Okay, and what is being plotted on this graph are two attributes of each model. Okay, one is the interpretability, and that is on the y-axis, And the second is the performance, which is being plotted in the x-axis. So what is the interpretability of a model? The interpretability of a model is the ability of a human being to understand why a model is making a decision. Okay? Whereas the performance of the model is measured by how often does the model make an accurate decision. So for example, if the model is trying to identify apples and mangoes, how often is the model correctly classifying the apple as an apple and the mango as a mango, okay, and not mixing up the two. So more accurate the model, better the performance of the model. And what you can see in this graph, and the entire purpose of showing this slide, is that there is a trade-off, okay? As models become better and better at making accurate decisions, the models lose interpretability, okay? And that's the reason for this negative trend that you see here. And even though like linear models and decision trees, like they are very interpretable, they do not perform as well, at least not all the time, okay? And this trade-off between interpretability and model accuracy or model performance forms the crux of the machine interpretability or machine explainability problem. And this is the reason why it's so challenging to solve this problem. So as you saw in the previous slide, models that are easily understandable by human beings by nature, and we don't have to do anything else, we don't have to create another mathematical model to understand the machine learning model. These models are called intrinsically interpretable models, and the two most common and popular interpretable or intrinsically interpretable models are linear regression or logistic regression for classification and the decision tree. Okay, so the way linear regression works is that you have a bunch of data points and you try to fit the best fit line across the point, and then that line that you fit helps you make a prediction about y using x. Okay, so it's very easy. You can understand that, like, you know, which factors or why the model chose x as the main predictor for y. And it's very easy for human beings to understand how the weights are being assigned to each x or each factor or each predictor. Whereas in decision tree works a little bit differently than linear regression, but still it's very understandable. So for example, here is an example of a decision tree, and you can see that it will start by asking you a simple question. Okay, so assume we are trying to identify different animals, and the first question the decision tree may decide to ask you is, does the animal have feather? And you say, yes, it has feather. And then it's going to ask you, can it fly? You can say, no, it doesn't fly. If it doesn't fly, then the model is going to decide penguin, which is very understandable why. Or, and as you can see that, like, depending on whether you reply yes or no, the decision tree is can ask you different questions. So for example, if at the beginning you said it has, your animal didn't have feather and took this branch of the tree, now instead of asking whether the animal can fly, instead it is asking you, does it have fins? Because any animal that is, like, you know, lives in water will probably, I mean, it makes no sense for them to fly, right? So the decision tree is following a systematic pattern of dividing the animals into water animals and animals that can move through air, right? And then if you say, yes, the animal has fins, then you take this branch and the decision tree says, okay, then your animal should be a dolphin. Okay, so now you can understand what we mean by interpretable models. The interpretable models tell us how they're making the decisions. On this slide, what I'm trying to show you is that clustering techniques too show a similar kind of trend, or like unsupervised learning models also show a similar kind of trend. where like, interpretability of clustering models or unsupervised models go down as their performance increases. And we are not going to talk about why that happens, because that would require more technical discussions. Just for now, understand that this trend in trade-off between interpretability and performance applies to both supervised learning and clustering techniques or unsupervised learning models. Now that you know what an interpretable or intrinsically interpretable model looks like, now we are ready to define the problem, right? The open research problem that I mentioned at the beginning of the lecture series. So the solution to this trade-off between interpretable and model performance, or interpretability and model performance, is that instead, because deep learning models or black box models can be so complex to understand, the solution that is most popular among researchers right now is that instead of trying to make the models interpretable, we try to provide post-hoc explanations for the models, for the trained model, okay? So what does post-hoc explanation mean? The post-hoc explanation means, if you haven't heard the term post-hoc before, is that we provide the explanation after the model has seen the entirety of the data, has learned everything it can learn from the data, okay? So the model has been taught, it has learned, and then we try to come up with maybe a second method or a second mathematical model to help explain what the model has learned, okay? So so unlike linear regression or decision tree that can walk us down the actual decision path that it took to come to a decision, here we are relying on something else other than the model itself to provide explanations after the model has been trained already, okay? So that's what post-hoc explanation means. And the gist here is that we want to be able to understand why the models are making the decisions they are making, while at the same time retain their high performance or high accuracy on data sets or on different, or in accomplishing different tasks. On this slide, I am providing some resources that you can use if you're interested in learning more about this problem or digging deeper into this problem of machine interpretability and explainability. And as you can see, like, different people take different approach. Some people have shown that certain deep learning model is equivalent to an interpretable model that we understand. In other cases, we use simpler models like decision trees or linear regression only to understand a small portion or a locality of the larger, bigger, and more complex deep learning model. In other cases, people are trying to teach particular concepts that we understand to machine learning models. So there are various approaches that people are taking across the nation and across the world to address this problem. And if you have any questions, or if you want to discuss this problem further, or you want to talk about one of the papers, or want help with reading through any of this paper, feel free to contact me. My email slide will be in the next slide. My email address will be in the next slide. Thank you.